A big hi to all the students. In our last two sessions, we discussed the S block elements. From this session onwards, we are going to start with the P block elements. And in this first part of our discussion on the P block elements, we are going to start with the first group of P block, that is group 13. P block consists of 5 groups: group 13, 14, 15, 16 and 17. In this session we are going to discuss only the first group of P block, that is group 13. It consists of boron, aluminium, gallium, indium and thallium. Since boron is the first member of this group is also known as the boron family. In the past, these elements have also been referred as the earth metals, and it is assumed that they existed before the existence of the earth. Another name of these elements is the trials. The word trials has been derived from the Latin word tri, which means 3, because group 13 was conventionally known as group 3b. These elements have the valential electronic configuration ns2 and p1, that is, they have 3 valence electrons. Now let's have a look at some of the general properties of group 13 elements. If we look at the metallic nature of group 13 elements, we will find that boron is a metalloid. By metalloid we mean that it is neither completely a metal nor completely a non-metal. It has intermediate properties. The rest of the members are poor metals. By poor metals we mean that as compared to the transition metals, these metallic elements have lower melting and boiling points, are more electronegative and are generally softer. If we look at the atomic radii of these elements, that we will find that there is a general increase in the atomic radii of these elements except gallium, as there is an addition of an electron shell with each period. Like atomic radius, ionic radius also shows an increase on moving down the group. The values mentioned in picometer are the ionic radii of these elements in their +3 state. On moving down the group, their boiling points also show a general decrease, because as we move down the group, we know that their size increases, causing a gradual decrease in the strength of the cohesive forces. The melting points of these elements do not follow a definite order. As we can see, the melting points first decrease from boron to gallium and then increase from gallium to thallium. Boron has an exceptionally high melting point because it exists as a polymer. So let's begin with the first member of this group, that is boron. The abundance of boron is low in the Earth's crust. It does not occur in its elemental form. It is found in nature in the form of its compounds such as boric acid, borax, borate, etc., which are together known as borate minerals. Its economically important ores are kernite and tincal. Its mineral form ulexite is in the form of fibrous crystal in which each individual fiber can guide light, as in fiber optics. Now let's have a look at some of the methods of preparation of boron. First method is by reduction of boron oxide. It is one of the earliest methods of preparation of boron. Boron oxide is reduced by metals such as magnesium and aluminium, and boron is obtained. This boron may have some impurity in the form of metal boride. Second method is by reduction of boron halides. Boron halides are reduced by hydrogen at high temperature to obtain pure boron. Another method is by decomposition of diborane. Diborane decomposes at high temperature to give boron and liberate hydrogen. Van Arkel method. In this method, in presence of tungsten and at high temperature, boron iodide decomposes to give boron, and iodine is liberated.